Hi, welcome to the lecture on Chapter 9, Wireless Metropolitan Area Networks. Of course, you remember from earlier lessons that a metropolitan area network, maybe it was even NET-125, you probably first heard about them. It's kind of like, what's one of the larger geographic areas that you could cover a wireless network in? And that would be like a city or a metropolitan area. So now it's cities like Lenore or something that have a network that covers the entire city, preferably run by a city versus a normal wireless carrier. So we're going to talk about defining what a metropolitan area network is, explain why they're needed. We'll talk about various features that apply. Whether it's the wireless technologies themselves, a little bit about what happens with free space, a little bit of microwave, standard of WiMAX gives you the higher speed, long distance communications, and of course we have to talk about security of WiMAX. So what is a metropolitan area network, a wireless metropolitan area network? It basically says I'm providing wireless connectivity across a substantial geographic area. And it could be as such as a large city. Now, of course, what's the primary goals of it? It's pretty much to provide extend wired networks beyond a given single location without having to install a wired connection. We may not see this a lot in the U.S., and granted, there's quite a bit of it, but think about third world countries that have wireless coverage. You always wonder how you can see a lot of the third world countries, all of a sudden they're on the internet, they're on, posting information on YouTube and on Facebook and stuff. It's because they can't afford the physical infrastructure to run cables to everyone's house to give them high-speed internet, but I can provide high-speed wireless connection. And that's kind of one of the major primary goals of a metropolitan area network. So I'm extending mobility throughout a metropolitan area. Just basically the big thing is areas not serviced by any other method of connectivity. Now, you sometimes hear the term last mile, and what it means is last mile wired connection. And basically it's what's the link between your house and the ISP. So there are different aspects. So if you're looking at using Charter as a provider, you've got your own local wireless area network, runs in and hits their cable modem. That cable modem hits what? Hits their landline high-speed connectivity, their coax cable running to their office. So this last mile is, okay, what's the connection between where the ISP drops off and where your stuff picks up. So that's kind of where we're talking about now. If you look at a lot of your ISPs, a lot of them are going what? They're going fiber. Pretty soon you may have fiber to your house, but right now most of us don't. The ISP provides fiber to a hub, and then it goes coax from a hub to other locations. Now, some use DSL, telephone companies, cable company, cable TV. So just gives you a rough idea. And this last mile is what happens from the time I get to the internet service provider's office to your home. That's this last mile they're sort of talking about. It may not be an actual building, but it may be a neighborhood hub that they've got fiber to, and then it goes off coax from there. But it basically means that you do got wired from here, but you may not have, so. Now, are there a lot of different options for that last mile? Absolutely. Depends on how much traffic, how much money you're willing to spend, how much guaranteed downtime you want. So if you're running a business, that has a lot of data, you may be thinking about, okay, how do I put in, excuse me, this last mile, which one of these would I pay for from my office to the ISP? What am I willing to pay, and how much am I going to get as far as initial cost and monthly fees if necessary? So as a business owner, you may make a decision as to how would I want that last mile to my ISP be paid for. Now, some of those, if it's a copper base, so if it's like a DSL, you're going to make sure that every 6,000 feet, the signal's got to be regenerated. So I've got to have to put a repeater in some device to kind of regenerate the signal about every 6,000 feet, so about a mile. So it varies based on who your telephone company is, what your ISPs are, how much cost you're willing to spend. But just knowing that since 1980 or so, fiber has been trying to replace as many of those as possible, as much as possible. Now, most technology used in this metropolitan area network, they can't afford some of these expenses here to pay to make connectivity between them. So what you're seeing is they'll use microwave at higher frequency bands between 3 and 30 gigahertz. And those towers are installed, and you probably see them, very tall, very big microwave dishes, but they'll range between 35 miles up to 50 miles to be able to communicate, to make that communication. So I don't have to worry about getting my signal to that microwave tower and let it handle it. It can handle a whole, 1,800 voice connections simultaneously. Whereas if I pay just for a T1 copper, I get 24. So in an area that is remote, I may say I'll put in one small wireless metropolitan area network, and I can have 1,800 people talking at the same time on one microwave tower than I could trying to think about running fiber or copper anywhere through there. So we just need to know that they've been used, this fixed wireless, this microwave is used in voice for data. It's used for backhaul connection, basically a company's internal infrastructure. Telephone companies use it themselves when they can't interconnect, along the highways. You'll see, especially if you go in places like Pennsylvania, even some of the mountain areas here, you can probably look and see a microwave tower and just kind of glance on the horizon and probably see another one, on the horizon, 4 or 5 miles away, to be able to make that connectivity. So now the question becomes, how do I want to transmit this? What is my broadband transmission, and what is baseband? Basically, broadband says I'm going to send multiple signals at different frequencies. Cable TV, for example. I mean, you got your cable TV. It's broadcasting, 200 channels, each one at a different frequency, all in that same channel. Now, baseband transmission says I'm going to take the whole transmission media as one channel. Now, that's similar to what the Ethernet does today. It transmits one data signal over, a single frequency. So, rough idea, broadband versus, baseband gives you visual. Now, landline fixed broadband wireless is definitely a good solution for last mile. It requires, some proprietary solutions and stuff, certain frequency plan, and in building, building to building location, you got a couple of different options. You can go point to point microwave. You can use 802, 802.16 WiMAX. You can use free space optics, which is, hey, what happens in free space? Now, basically, okay, what is free space optics? Free space optics is it's a point-to-point line of sight technology. It's definitely a good alternative to high-speed fiber. It's definitely cheaper. I can transmit 1.25 gigabits up to 4 miles, about 6.4 cap in full duplex mode. Now, it uses infrared instead of RF. So it is definitely, but you gotta have, this is the key, line of sight. So you think about it, you gotta have your transmitter and your microwave, your antenna receiver perfectly aligned, and you can think of how difficult that may be, at least as far as installation is concerned. And here you see, you've got this free space optics, and you can tell the way the antenna is designed, it's very focused. So one, I'm generating a lot of signal and aggression, but I'm going to aim it very specifically in a one particular target area. So you can't miss it. So this isn't like a parabolic dish where I'm capturing a lot of data and trying to funnel it in. I'm narrowing. This is a very narrow focused beam of information. Now, some of the advantages definitely cost less than installed fiber. The speed of installation. Other than getting, two antenna installers sitting up, 200 feet in the air, it pretty much means in a matter of days I can install that connection. Now, and the transmission rate, it definitely can be scaled to meet, particular users' need. And it's definitely, because of infrared transmissions, it's definitely more secure. Disadvantages, if it rains, if it snows, that does have an impact. Based on light densities, atmospheric disturbances, all of that interferes with the data. What happened about fog? What about signal interference? Tall buildings, that all of a sudden you thought you had it lined up and it really got a windy day, and actually a really tall building actually swayed a little bit. I don't know if you've ever been on top of the Sears Tower or something like that on a windy day. It'll actually move and you can feel it. But if that movement, if you haven't accounted for that in that free space optic design, it may affect that beam and connectivity. Just gives you a different idea. Now, applications, last mile connections, local area network connections, fiber optic backup. It's great as a redundant link. And backhaul, it says, hey, when I don't want to pay for high speed connectivity, I can use that as getting way back to a tire. Now, another option is microwave links. Now, those are a group of wireless technologies that have come a long way, but interconnect cell towers, buildings, intercity networks. Now, it uses electromagnetic waves, which is similar to, but its wavelength is smaller than what we use in other wireless technology. Now, permanent microwave links definitely are point-to-point. Line of sight again, permanent. Now, they're operating in 18 gigahertz frequencies. Can get data rates a little bit faster, between 2 gigahertz and, 2 transmitters up to 4 gigahertz gigabits compared to what we saw in the free space optics. Now, it uses frequency division duplexing, one frequency, receiving on one, sending on one, receiving on another. Most microwaves can handle all of the IP traffic, so it isn't a split between two. It uses orthogonal frequency division multiplexing to encoding. They're very today the transmitters are very compact, installed on towers right next to antennas, and you see that in some of the smaller businesses out there. Actually, your homework assignment this week is going to get you a chance of observing antennas and what you can and can't do with them. Just gives you a rough idea what one looks like. But as you notice, look at the design of this. So it's a little bit broader target as far as transmitting and receiving. So it's just a little bit different. Now, it's great. Microwave links are great for temporary links, sporting events, Olympics. They can come in, set up small cells, transmit back to either all the telephone communication that's going on to the broadcasting of the event is all going close by, by wireless, and I don't have to run cable every time I move to a football game or to set up a new sporting event. They can transmit not quite as fast, but I can multiple 100 to 200 megabit lines. They can be non-line of sight in some cases, but if they are, single point, I can get up to 600 megabits. Now, the open standard for wireless broadband for this is 802.16. So if you're looking for setting up a metropolitan area network, you can use the WiMAX standards. It stands for World Interoperability for Microwave Access. It can either work line of sight or non-line of sight, depends on which frequency you're going to use. It's introduced in about 2000, trying to standardize some of the communications. It supports enhancement inspections to the MAC protocol. So it's possible that if you wanted to have a base station communicate to another base station or a subscriber station, laptop to a device, all of that, since it's following the MAC protocols now allows me to do what? I got layer 2 connectivity, so I don't care about anything else above it, so I can support Ethernet communication, where free-spec'd optics, it can't support that kind of communication because of the directional requirements. So it does have some flexibility that it has. Gives you a rough idea of some of the equipment. This just happens to be a lab setup, but you see base station, installed close to the antennas, and then you see integrated antennas along with a controller that's controlling the activity, how much stuff is going in. Now, the WiMAX forum, it's a group of people that help implement this 802.16 protocol, doing testing and certifying it. It makes sure that the standard offers multiple RF interfaces at the physical level, but they're all based on a common MAC protocol. I don't know where my mouse goes. The MAC protocol, so that that at least so I can change the layer 1. So what do I have to do? I got to worry about that MAC protocol. Remember that was divided into 2 sub layers at the layer 2. So one to handle the different physical interfaces, and one to go back to interface back up the network layer. So that's what you're seeing here. Is now I'm allowing the 802.16 allows different standards for the physical interfaces. Now, some of the applications of this, you've got again, the last mile can definitely replace T1 DSL cable modems. Definitely supports simultaneous voice, video, data, suitable for voice over IP. So it can allows the convergent of voice, video, data. So it handles everything what the IP, the internet service provider wants to sell you, right? You get that bundled package. Now, some of the applications, it allows vendors to create different customer premise equipment. So that way I'm not worried just about the ISP to lock me into their equipment. It can be installed as a point-to-point. Some WiMAX CPE devices support all 3, video, voice, and data. It just depends on, what services you're looking for, and definitely as time goes on, the price and what services are offered has dropped significantly. It's one of the advantages of a standard, right? So everybody can build to a particular, they know the rules, so now anybody that can come up with a better mousetrap can offer it and forces the market to reduce its cost. Now, having that MAC protocol layer interface, it allows easier for carriers to deploy a network. Once a base station's installed, the end user can just take a piece of equipment, CPE equipment off, go to Best Buy, pick it up, turn it on, and done. They've installed because of what IEEE has done with the interfaces and the rules in the protocol of the MAC layer and the physical layer to make sure all this stuff makes it relatively easy. Now, the range, instead of just being measured in kilometers, it's, you know, or in when you're talking about a normal Wi-Fi, you know, we're talking about what, 100 feet, 300 feet. Now we're talking measured in miles, in kilometers, as far as its range. So it definitely goes out. Now there's definitely a whole series of standards that 802.16 has come up with. 2001 came out in 2000, so you got subcategories in 2001 to 2004. And basically all they do is, what am I doing? I'm increasing speed. I'm trying to get better security, but just gives you a rough idea of, you know, how I do mobile versions, how I'm going to enable data rates up to 2 megabits, trying to get themselves back up to 100 megabits. You know, started getting to that landline physical cable speed. Now, the protocol stack, the different layers, you got the physical layer, which supports multiple frequency bands. Physical layer is able to adapt on the fly based on what you're connecting to. The MAC layer, it's connection oriented, so it is going to, the conversion of the different sub layers. So I've got one layer that's dealing with the upper OSI layers, and then one layer in the MAC layer is dealing with the physical. So as the physical layer is changing, I've got to make sure that that MAC layer can handle it. Offers different services, IPv4, IPv6, Ethernet, LAN, and a whole lot of others. So you can see this is becoming a very profitable venture. So this gives you a rough idea of what that protocol stack looks like. So you got your physical layer, your MAC layer, which they've got broken down a little bit further, and then you got your other upper layers, which what's that? The network layer and above, transport, application. So your physical layer, different variations. Transmission is half duplex. Each frame is subdivided into uplink subframe and a downlink subframe. You may see the term burst, which is just sending a bunch of data from a single device. Time division multiplexing, what am I doing? I'm taking uplink or downlink parts and I'm dividing it by time, how much time each application gets. So I'm taking one whole frame structure and split it in half. So I get some for the uplink, some for the downlink, and divide each one into a particular time slot when they can produce. Now, frequency division duplexing, it's used one frequency on the uplink, another one on the downlink. WiMAX FDD can support half or full duplex. So it's just something you need to keep in mind if you're going to use this way. Now, one of the older wireless technology from the telephone company standpoint was using time division multiple access, TDMA, which allowed you to set up frequencies for given time slots. Now, 802.19, this is in future stuff, well, not so much future, but it's 2009, so it's one transmit mode. It allows me to create a wireless MAN point-to-point communication, either time division or frequency division. Now, the standard also applies for non-line of sight. So there are other options in that protocol stack. So just giving you a rough idea. So if you wanted to, you could create an environment like this. Line of sight or non-line of sight. The line of sight says, yeah, I've got this antenna. I got to have direct line of sight over top all the trees. And the non-line of sight CPE equipment, I'm just bouncing it off anything and everything to hopefully get something that'll come back up there. Now, there are additionally other transmissions for non-line of sight, OFDM, OFDMA, all of those are things we've talked about in the past. The high-speed unlicensed metro area light network, that wireless human based on OFDM, but now it's using an unlicensed 5 gigahertz frequency band. So there's definitely choices as far as what kind of applications, what kind of frequencies, and what kind of duplexing that you've got available to you. It definitely has its own modulation and error correction. It uses forward error correction, which says it inserts additional bits in the data to enable the receiver to detect a multiple bit errors and then correct them. So the math on that becomes pretty impressive. 802.16 also has automatic repeat requests. Just make sure the reliability is up. Now, it was designed, this 802.16 protocol was designed to achieve, remember the 5 nines as far as reliability, 99.999% reliability. So it can use different coding rates, modulation rates. So you got a whole lot of options as far as how you want to code it, which as you change these, as we've seen earlier, how much data I'm going to get on a particular set of bits. So I've got modulation and error corrections. I can actually, take into consideration how much latency. I can try to reduce that latency, how much time of delay is in there to improve that service. Gives you a rough idea of what that protocol looks like and is who would use which options. So maybe to a hospital, to a home or something, I'd use some slow speeds, but if I was using a building or a factory or a warehouse, I may want to use some higher speeds. Now, WiMAX has what they call WiMAX profiles, and it's just basically a predetermined set of parameters that can include what information you want, frequency channel, bandwidth of the channel, transmission modes. It just helps initiate for support and a quick installation. So I don't need to have a lot of on-site setting up parameters. I'm just saying, hey, we're going to use profile 1. Boom, roll it off. Pretty much turn it in, plug it up, turn it on, and we're off and running. So you got system profiles, you got burst profiles. What happens as far as negotiating between base stations and service stations? Which way are these going to go? Now, range and throughput, it depends on the amount of frequencies. The higher frequency you use, you get higher data rates. Lower frequencies, you can increase the transmission distance, but then I reduce the amount of data that I can push through. Your choice. So gives you a rough idea. This table kind of says the data rates and the channel bandwidth that you have as far as what choices you've got. So based on what you're designing, you're going to pick and choose which of these you're going to play with. Now, the MAC layer is typically implemented on a point-to-point, point-to-multi-point basis. One base station potentially pointing to hundreds. So it allows to allocate, this bandwidth according to the service station. Now, the advanced antenna system, multiple signals transmit over different directions to the stations that fall within a certain range. So WiMAX can take advantage of multiple, that MIMO, multiple in, multiple out antenna systems, which of course reduces that interference with other networks. To address bursts, it can use a 16-bit connection identifier. So there, as you can tell, there are a lot of different options you can do to set up WiMAX to allow this metropolitan area network to be as redundant, as reliable as possible. As far as security is concerned, as with any wireless system, security is always an issue. Free space, it's generally considered secure because sniffing that information, now because those are what? Infrared. It makes it difficult to sniff out information. Microwave security, each microwave vendor implements its own. 128 or 256-bit AES encryption is probably the norm. but you still need to choose. The MAC layer includes privacy sublayer. That privacy sublayer provides client-server authentication using digital certificates to identify the authority. Components of the privacy can be encapsulation, a privacy key. You can have a traffic encryption key, a key that's used to encrypt the data, and must renew this key periodically with the base station. Usually default lifetime of each one of these keys is about 12 hours. Multiple different types of encryption algorithms, from 128 on the low end to 3DES, triple DES on the high end. So it's you can encrypt and put a lot of security in. So in summary, you got wide array networks, a group of technologies provide wireless connectivity throughout an area, a large geographic area. It's that last mile is, that how am I wiring up between the customer premise and the ISP. You've seen different types of transmission. You've seen land-based fixed broadband wireless techniques, from free space microwave to WiMAX. Went into a lot of detail on the WiMAX protocol itself. So just giving you a rough idea of some of the security, some of how scalable it is, the MAC layer. So you've probably learned more about wireless metropolitan area networks than you ever cared to know, but it'll help you in the test. If you have any questions, let me know. Bye-bye.